I started the video recording, so let me share the screen. 1 second. Hello, good afternoon. Okay, so first of all, I had a conversation with Professor Archetti about the exam dates. And if you agree, you are a few students only. So I think we can take an agreement, a verbal agreement, and then if you need additional dates, I think the best thing is if we agree verbally on the first date. Why orally and not in a written way? Because I think that you may want to have an opportunity to take the exam before the official date, before the official time window is opened. In principle, we cannot register the exam before June 10, because we cannot register exams before the end of the lectures. But actually, given that we are actually finishing the lectures well before June 10, because I'm finishing on May 8, as you may remember, and Professor Archetti, I think she's finishing more or less the same date. So we think that you may appreciate an opportunity for giving the exam in May, but in this case, we cannot schedule it in Al Mesami. We cannot register the exam before June 10. So in a way, you have to trust us that we will register on June 10, and you will see in your official record that you took the exam on June 12, 10 or 12, or whatever we schedule it. So if you are happy with the solution, the first date needs to be agreed informally. And we have an opportunity for May 15, which is a Wednesday. And in the morning, Professor Archetti is here because I think she's organizing an event. I think it's a seminar or something like that, or a visit. And then in the afternoon at around 2 p.m., we could make the exam, or the two of us together. So are you interested in this date? Because of course, if you say, no, I'm not interested, we don't fix it, but we don't schedule it. But if you are interested, what is your feeling now? Are you interested? Yeah, and all of you. Okay, no problem if you change your mind. Just to know if it is worth scheduling it. So let's fix May 15. It's in my agenda. And it's a Wednesday, like today, 2 p.m. And then if you need any additional information, just let us know. Of course, we will see each other again for the last lecture on May 8. I'm sorry for this long break, but I am away 2 weeks. And then May 1st is a public holiday. So if you have any additional thought on that, just let us know. And for the next dates, I think that the best solution is that we agree individually, because you are so few students that I don't think it is productive to schedule dates. We just let us know when you would like to take the exam, and then we will schedule it in Al Mesami, and you will be able to subscribe formally on Al Mesami, because the next dates will be like mid of June, end of June, July. We are committed to take the dates that fit best you, okay? So to summarize, May 15 is the first opportunity. If you don't take the exam on May 15, or you decline on May 15, just contact us for fixing other dates in June and July. And one last question, is it clear? Okay, so you select, you choose. I mean, it's not necessary that you take an agreement between you, because my feeling is that you may take the vast majority of you are 5 students, and maybe someone more that it's not attending physically the lectures, but usually we have like 7, max 10 students, And my feeling is that most of you will take it on May 15. And then the students who remain, like 3, 4, we can take an agreement, okay? And this is perfect. And one final question. For May 15, we are fixing the exam here. For the next dates, if you want to take the exam in Bologna, for us, it's even better. And maybe that it is the case that we ask you to please come in Bologna if it's not a problem for you. Because in this way, you know, our offices are there. In this way, we can better fit our agendas. Everything is clear? Very good, perfect. And okay, now let's move forward. So one first thing I want to discuss with you. I'm sorry, as you know, last Wednesday the lecture was a bit confused, and the reason is that as I will tell you, there was a mistake in my lecture notes, which I want to discuss now with you. This is one of the reasons why I got confused. And also, it was not a good day for me. I was not feeling really well. So what I want to do today, 10 minutes, 15 minutes, is to go back to what we discussed, because I wanted to clarify any doubt, any obscure point, any doubt that you may still have, okay? First of all, I want to start from the end of last lecture. The end of last lecture was the exercise. I think the exercise was fine. The only thing is that it was very quick. So I understand that in doing that so quickly, probably it has not been the best thing to do. Just to remind you, the exercise is to compute mooring forces after a ship is forced by wind. And of course, wind over the ship means that the ship gives a forcing along the mooring lines to the bollards, and we need to compute it. This is the subject of the exercise. It's extremely relevant to Harbour engineering. So computation of wind forces, I think it's not a problem, because it's just one relationship, which is somewhere here, and this one. And I think you understand it because it's very simple, and we discussed it previously. So this is the first part, is very simple. And then there is the computation of the rotational moment, which is, again, I think quite simple, because you take the wind forcing and then you multiply it by the eccentricity, which is calculated based on information from the producer of the ship or information from the literature, like in this case. Okay, and now, the step that was very quick was the computation of the mooring forces, the mooring forcing, sorry. And in particular, I just want to emphasize once again, this is a problem that is usually dealt with in structural mechanics. It is a complex problem because the mooring lines are elastic lines. They are not rigid constraints. They are elastic, so you have to take into account the elasticity of the mooring forces, of the mooring lines, which depends on their length. And so the problem is quite complicated. But most importantly, it's a problem of structural mechanics. And therefore, the purpose of the exercise was not to clarify and to make you learning the procedure, the structural mechanics procedure. The purpose of the exercise was to show you the procedure, the relationships that you should apply. There is an R code that is proposed for that. You can reproduce this exercise by just cutting and pasting the R code. What should remain in your mind then? Not the relationship, not the analytical formulas, which are quite complicated. It should remain in your mind the concept of the procedure. So how to compute mooring forces along the mooring lines. So the concept, I think it should be clear from the exercise. Basing on the wind forcing and the rotational moment, there is this procedure of structural mechanics that through subsequent steps allows you to, okay? So what is the question that you may find at the exam related to this? Just questions that can be discussed orally, like the name of the mooring lines. You may remember that we discussed it. after spring, and several other terminologies that you find in the previous lectures, not here. In the previous lectures, there are, in the terminology, there is the clarification of the names of the mooring lines. Try to make an effort to remember them, and try to make an effort to explain the concept if you are asked. Like, I first need to compute the wind forcing. How do you compute it? The relationship, it's one of the few that I asked you to memorize. How do you compute the rotational moment? And this is basic concept. And how do you computing the mooring forces? And it's just enough that you say through a procedure that is based in structural mechanics that allows me to take into account elasticity of the mooring lines and then to find individual forcing over all the mooring lines. And one thing that you may say is that, of course, if you compose all the mooring forces, you should find, like it is done in the exercise, you should find, as a result of the composition, the wind forcing, because, of course, the mooring forces are just the translation of the wind forcing along the mooring lines. So if you compose the mooring forces, you should find the wind forcing. And this is the check that is done at the end of the exercise. That's it. Okay. Do you have any questions related to this? Is it clear? Okay. Now, let me talk about Harbour oscillations, which I think, after thinking at the lecture that I gave, that it's clear to you what happens. It's clear to you what happens, let's say, in principle. You have waves entering into an harbor, okay? So up and downs of fluid particles. These waves get, after some time, at the end of the harbor, what we call the head of the harbor. The entrance, we call it also the mouth of the harbor. And then they get against maybe a seawall, which is, or a pier, which is the end of the harbor. When the wave gets against this seawall, it gets reflected back. And it takes some time to travel along the harbor and to come back. Okay. Now, if this time of traveling is the same as the periodicity of the wave forcing, then you may get in trouble, because we demonstrated, and we will see again that the reflected wave then may resonate with the incoming wave, which means that, first of all, what we call the stationary wave develops, and then if the forcing from the ocean continues, the forcing from the ocean may amplify continuously this stationary wave. Let me show you a figure. Okay, one of the figures that I think is clear. It is this one. Okay, here what you see is the blue wave traveling from the left to the right. The left is the mouth and the right is the head. And then you see the red wave traveling from the right to the left, from the head of the harbor to the mouth. And you see what is the result of this superimposition. It is a stationary wave, the black line, which goes up and down with apparently no movement. This is why it's called a stationary wave, no movement in the longitudinal direction along the horizontal axis. There is only the up and down, while the other two waves, the blue and the red one, there is an up and down, but there is also a translation. Okay. And this stationary wave has an amplitude that is twice the amplitude of the incoming wave. Okay, so if you get a wave entering from the ocean, and this wave is maintained for the necessary time to travel to the head and travel back, okay, the result is this stationary wave of the composition. And then the stationary wave continues. I mean, even if from the open ocean you stop the wave, okay, so the wave lasts just for the time to go forward and back, and then you stop it, like you may remember the video in the lab. There was a wave generator working, and then they stopped the wave generator, stopped after the stationary wave had formed, okay? If you stop the wave entering into the harbor, still the stationary wave continues. And if there is no damping, if there is no dissipation, it continues forever, okay? Actually, we have dissipation, so it's not forever, but still it continues for a while. Now, after the stationary wave has developed, if the forcing from the ocean continues, the effect is a continuous amplification, and this is what we call resonance of this stationary wave, okay? And this is what we want to avoid. So it has been demonstrated in some observation, in some situations, that the height of the wave entering from the ocean has been amplified up to factors of 4 to 10, even to a factor of 10. What does this mean? It means that if you have a wave entering from the ocean that has a wave amplitude of 1 meter, then after a while, if the wave entering into the ocean continues, you may get waves that have an amplitude of 10 meters. These are exceptional situations, okay, exceptional. But this is what may happen. And what is the typical period that is concerning us? You know, I said the period of the wave should be comparable, very close to the time the wave takes to travel back and forth. So if the harbor is huge, some harbors are like a couple of kilometers long, the period may be very long. So the waves that can cause the resonance are waves that you can barely see them, like tide waves with a period of 12 hours. So there is an excellent example, which I may show you, of a bay where the period of the tide is 12 hours, and it is matching the travel time of the wave back and forth. And therefore, even if the tide is in open ocean, like 1 meter, then you get a change of level into the harbor that is much more than that, okay? And let me show you this example of this bay. I think it is called, let me just, because I don't remember the name. If I search for resonance harbor, it should come out, because it is a striking example. And let me see, mechanism, harbor resonance. I should find it. Okay, let me see here, the first link. The first link is interesting. It is linked from my website. So let me see if there is here. Let me see, resonance bay. Because actually the example I'm talking about is a bay, not an harbor. Foundy, okay, Foundy Bay, resonance, tidal resonance Bay of Foundy, okay. And here there is, there are several links, and it is called the highest tides in the world. And let me see if there is a map. No, it's not here, it's NASA, NASA. These are several pictures. Here you can see a picture of the bay. As you see, it's very long. The Bay of Foundy. Let's see, and this should be an image. As you see, the bay is very long, and there is an excursion in this bay of the tide that is up to. You see, most of the U.S. coast has a tidal range of 1 to 2 meters. And here, the geometry of the bay causes the tidal resonance, which plays a key role in elevating tides. The bay is just the right width and depth for water to slosh back and forth at a frequency every 12 or 13 hours that matches the natural frequency of high tides, which are driven by the gravitational pull of the moon and sun on Earth. So, since the Bay of Fundy becomes shallower and narrower, incoming tidal flows get forced especially high as water piles up behind the mouth of the bay. And basically, the excursion reaches the height of 20 meters. There is written something. And of course, in this case, there is another component. It's not a simple case like we considered of a rectangular bay. This is getting narrower as we get into the bay and less deep. And therefore, it is also amplified the effect by other types of reflection. So it's a 3D problem. We consider the rectangular bay, which is a 2D problem, and then you have only one reflection at the head. But if it is converging the bay, you get a composition of different reflections. One final thing. We said that the stationary wave that develops is characterized by nodes and antinodes. Nodes are the red point here. They are the points that are fixed. And the antinodes are the points with the max elevation or depression. Okay, so the antinodes are located at the crest and through of the stationary wave. The configuration for an open basin is such that we have a node at the mouth, at the entrance of the bay. Why a node here? Because here you have a reflection operated by the ocean. And the ocean, after the waves from the ocean have stopped, is fixed in level. And therefore, the stationary wave, the wave that is reflected back, gets reflected by a liquid body, which is fixed. And this causes the presence of a node. On the other side, at the head of the wave, instead, the wave is free to move up and down. And therefore, we have an antinode there. So if we want to describe this phenomenon mathematically, we have to impose these two features: a node at the mouth, on the left here, where is my mouse, and an antinode on the other side at the head. So when we write the equations, and this is what generated part of the confusion last time, we have to impose these two features. Okay, and how we impose it? By changing the phase. So basically, you have two waves traveling. One, the blue one, from the left to the right, and the other one is traveling from the right to the left. So you have to, in a way, combine their phase so that their composition generates a node on the left and an antinode on the right. Okay, so given that we entered into, first of all, before we talk of the mathematical description, we have learned, and I think this was clear, that there might be waves with different periods that generate resonance. Okay, so there are long waves generating resonance, but we can have also waves with shorter period. And you may remember the video with the guy that was agitating the string, was moving the string up and down in order to create along the bay 0 nodes, 1 node, 2 nodes, 3 nodes, okay? And I want to refer this figure, and let's look at the open-ended basin here. You see that we have the case of the fundamental mode, which is called the Helmholtz mode. No nodes. Okay, we have the node at the mouse, but no internal nodes. So number of nodes, 0. And you have this wave that is developing, okay? Up and down, okay? So it remains fixed at the mouse and goes up and down with these two extremes at the head. If we want to get one node, this is the geometry of the wave that is developing, up and down again, okay? So you see same configuration, a node at the mouth, an antinode at the head, up and down. If we want 2 nodes, this is the configuration. And same configuration in general, a node at the mouth, an antinode at the head, okay? And Marian's formula gives the period depending on the number lowercase n of the nodes. L here is the length of the harbor. Okay, so if you have an harbor that is 100 meters long, what is the period of the fundamental node? N0, it's 4L, 4 times the length, divided by the celerity of the wave, GD. G is gravity, D is the depth of the harbor. We are assuming that the harbor has a uniform depth, remember. In our computation, we assume that the harbor is rectangular with uniform depth. So 4L divided by celerity, GD squared, square root. And then here, if n is 0, this fraction, this ratio here is just 1. So the fundamental period is 4L divided by the celerity. If you increase the number of nodes, you get period with decreasing amount. So it may be interesting to look at the mathematical description at this stage, because the mathematical description allows us to understand what's going on. Okay, so the question is, let me go back to this figure. There are several figures. I mean, this one is, I think, the clearest one. If I go up, you see another figure here with several nodes, etc. And so how can we describe these waves analytically? There is a simple approach, which is reported here, two simple equations. These ones, and here there was a mistake, which brought me to make the confusion, okay? The mistake was that here, where you see lambda now, I put capital L before, capital L length of the bay. Absolutely, it's not the length of the bay, it's the wavelength that should go here. So I changed the symbol because I wanted to make clear that I made a change here. So what happens if I combine these two equations? And I think the best thing to do in order to see what happens if I combine these two equations is to try to apply them with R. And then with the application, I will show you how to impose the condition of the node at the mouth and the anti-node at the head. Do you have any questions so far? Everything is clear in what I corrected? Okay. I mean, I think it is interesting to try to understand because first, this is a phenomenon that may be important in Harbors. And if you look over the web, Harbor resonance, Bay resonance, you understand the importance. You will see several links. First thing, it is important. And I mean, it's not necessary that we really learn everything of it, but to understand the concept is important. And today I'm trying to focusing on the concept. And second, I think it's also fascinating because, you know, it is fascinating to think that under certain conditions in harbors, something like a monster can develop. Okay, it's anyway interesting. Okay, so let's get the R code, which should be somewhere here. Let me see, where is it? And let me open an R window. Let me see, code. Okay, here is the code. Let me open it in another. We don't need to open RStudio. I think it's just enough if I get a console. Okay, let me just 1 second. Here it is. And let's change the font in order to make it more visible. Okay, good. I cleared the screen. Now let's take the code. And first of all, in calm conditions, here there is an introduction, which is something like a tutorial to generate the picture of calm conditions. Let me copy it. And it is a stupid exercise. I mean, it is very easy. And there is nothing to see here. Okay, this is calm condition. First of all, look. The Harbour is supposed to be rectangular with constant depth and with a length of 100. The units, let's forget the units, okay? Can be 100 meters, 100 kilometers, whatever, okay? 100. And this is indicated with the symbol LL, okay? Perfect. And we put 0 the level, the altitude of the mean sea level. In calm condition, you have this situation. Perfect. Now, let's go down in the code and let's generate a standing wave. And here, let me just copy and paste, and then I want to show you what happens here. But first, let's have a look at what happens, okay? This is just the code of the application of the two equations that you have just saw. It's nothing different, okay? And if you look at these two equations here, and it is precisely the equation that I have shown to you here. Precisely these two equations for varying x and varying t, okay? The only thing, but let me just tell you later what is the only thing, okay? Okay, now let's see, this is this, I'm sorry, it doesn't work because I didn't make a change. You can see the stationary wave only for a short while. Let me see if I can change it quite quickly. Second. Okay. So for this, there is a delay here, a delay time, which is okay. Let's move forward with the correct order. Let's do the incoming wave, simulation of the incoming wave. Incoming plus reflected, okay. Okay, good. Let's make this one. I think we can avoid the second one that is below. Okay, I clear the screen and then, okay. You see here the standing wave. Finally, it came, but it came only at the end. So let me just show here. Okay, this is the picture of the incoming wave. And then let me see what's going on here. I think I didn't change the code. I don't understand why. Okay, let's focus on the equation. I don't understand why it's not showing the progress. I think the reason is that the computational time, it is too small here. Let me just check. But before I check what is the visualization problem, let me just show you the computation. So these are the two equations, okay? These two equations here. In these two equations, be careful. Here we have the one only difference between equation 1 and equation 2, which is the minus and the plus sign. And the minus and the plus are placed just before the progress of time. So what is the only difference between these two waves? It is the direction of traveling. So here, if you put the minus in the first equation, you get the wave traveling from the left to the right. If you put the plus here, you get the wave traveling from the right to the left. And there is no change of phase here. You see, the only change, the only difference is the direction of traveling. But there is no change of phase, which is what we want, because we know that at the head of the Harbour, we have no change of phase, and this is why we have an antinode. At the mouth of the Harbour, we have a change of phase in the reflection, and this is why we have the node. But here, the only difference is the minus plus, which is on the direction, okay? Now, how can we then impose the node at the mouth and the antinode at the end? Let me just use this figure, given that my visualization has some problems. Let me use this one. You see that here, the way to put a node on the left and the antinode on the right is to shift the x-axis and to limit the x-axis in a way to have x equal to 0 placed in correspondence of the node and x equal to L placed in correspondence of the antinode, because this wave is a wave that may last forever. You just have to make sure, if you want to create a resonance, to describe mathematically a resonance, that x equal to 0 is on the left in the presence of the node, and x equal to L is on the right in the presence of the antinode. And how do you obtain this? You obtain this by, in this code, one second, in this code, by changing the x-ordinate accordingly. Okay, so you see that here I added this quantity, SF. It is a translation of the x-axis in order to get the node on the left and the antinode on the right. Okay, and of course we have to put a proper value. Now, I don't understand why the visualization doesn't work, and this is a pity. I need to check it. Why? Because with the visualization, we could see the effect of how the wave behaves by changing the number of nodes. Here I put nodes equal to 3. So let me just check if I can make this working once again, because I am sure that it is correct. And if I cannot get it working here, maybe that I can, let me see, but still it doesn't visualize. Let me just stop it. Okay. I don't understand why AB line is only at the end. Let me just check here if it works on this PC. Because if it works here, I show it to you here. Give me 1 second. I am running it here. Postal code wave. Here it is. Let's see. Yeah, here it works. Okay, let me just then. Yeah, it works. Okay, let me then. I'm not sure if I can connect the PC directly. Let me just check. I think I can. Perfect. It was quite easy. Okay, now the mirror display was okay, good. Okay, so let me just put it in a way that this is the R console. Let me just change preferences. It is curious that it doesn't show up here, and it's really curious. Okay, so here is the font. Sorry? No, it's okay. Thank you. Okay, so close. Okay, this is the R console. Now let me. Okay, let me start this. This is the code taken, but I don't understand why. Paste. Okay, paste. Okay, should be here. This is the incoming wave, as you see, and then it gets reflected, and you see the composition that is generating the stationary wave. And this is the final result. The blue is the stationary wave. Let me just expand it, and then let me repeat. So the black line is the entering wave, and then it gets reflected with no phase change. And you see that the blue wave reflected is traveling, the red wave reflected is traveling back, and then it gets superimposed to the blue wave. Now, it is interesting to see what happens if we change the number of nodes. Let's put the number of nodes equal to 5. So let's increase it. One second, okay. And I don't understand. Okay, let's see. You see that here we have more nodes. One, two, three, four, five. 5 nodes. Okay. we can try also, I didn't try, let me try if it works with n equal to 0. Could be a bit, it is a singularity, so let's see. We shouldn't find any node if it works. Yeah, this is equal to 0. And this is what you found here. Okay, I cannot look at it, but if you look, remember the figure with the different number of nodes, and of course this is the way for half a period. If you want the full period, you have to continue the simulation. This is half a period. Okay, it's the travel is 2L. Now, what happens if I change the phase? You see that here the phase, I mean, the shift of the x-axis is 1/4 of the length. Can you read there? It's not easy. Let me just change the font. Okay, good. So if we put, for instance, SF equal to 1, so we basically shift the waves, the two waves, one with respect to the other. Let's see what happens. And let's put also the number of nodes to 5, or let's see, 3. And then I cut and paste. So at the beginning, nothing is different, but you will see what happens at the end of the story. You see that the stationary wave is not forming. They are both traveling back. And at the end of the simulation, there is no node, antinodes, and the stationary wave didn't form. This is because basically by changing this position of the x-axis, I moved one wave with respect to the other. So what I need to find is the correct position along the x-axis of these waves. And let me just check if the standing wave works, because this code is generation of a standing wave, generic one. Let's see. Yeah, it works. You see that here we have a generation of a standing wave without propagation. And this wave, I mean, can last forever. Okay. You see the blue one is standing. But what I need to do is to place at the beginning a node, at the end an antinode. And if I change SF, it changes the position. Okay. That's it. Okay, let me close here, and then we can move back to okay, perfect. And move back to our screen. Okay, so what is the moral of the story? Moral of the story, let's go back to our web page. So we try to summarize everything. I will try to understand why it doesn't work here. Maybe it's the difference is Windows, I don't know. And I will try to understand. Meanwhile, you can try on your PC, maybe it works, I'm not sure. And it's only a visualization problem, probably because in order to make the visualization, I put a delay in the code, and you can find the instruction of the delay here. here, you see that at the end of each code, there is a while, this instruction. And this is a delay instruction. Basically here, it takes with the first line, the time of the system. And then here, this while is an instruction that pauses the computation until the time of the system is advanced a couple of seconds. So each round is advanced a couple of seconds. So maybe that what we need to do is to change this number here, 4.05, which is the delay time. Maybe that it works just changing the delay time. Good. So what is the moral of the story? The moral of the story is that this phenomena here, I think, I hope that you understood now the concept, how it works, can be described with these two equations. And these two equations, however, they need to be, the x-coordinate needs to be set in the proper way to make sure that we have a node at the mouth and an antinode at the head. If you can please remember these two equations, because these are basic equations in wave, describing waves, I would appreciate, but it is the only thing that I ask you to learn about here. So the composition of the two waves, it's not necessary. This is the equation of the standing wave that derives from the addition of these two waves here. So it's not necessary that you learn this, just these two equations, okay, incoming wave, reflected wave. And remember the fact that at the head of the Harbour, you have a reflection with no phase of change. At the mouth, we no change of phase. And at the mouth, you have a reflection with the change of phase, okay? I think it is just enough. And then I think we can close here. Yeah.
The waves come near the rock and run off, and after that, back to the sea. Does it happen?
Yes, it basically, the reflection happens when the wave moves from a media, in this case the seawater, against a media with different density. So the reflection also happens when the wave from the bay gets into the open ocean. And it's a media with, it's not a different density, but it's a media that is, in a way, it's not moving. It's not moving, it is fixed, and therefore you have a different reflection with respect to when you hit over a wall. But to reply to your question, yes, when the wave gets against a rock, it gets reflected in the same way. However, the rock is not regular. The geometry of the rock is not regular. So the reflection is not right, a plane reflection like we get here. And I think that you should have studied the reflection of waves with Professor Archetti. We didn't study the phenomena of reflection in general. Usually, for instance, what happens is that in reality, let's suppose that you have the wall here, the head, okay? This is the head. We assume that the wave, the crest of the wave is aligned with the head. Let's suppose that it's not. So what happens if you get a wave that is hitting here, okay, with an angle, okay? So what happens is that the wave gets reflected, but it gets reflected in this way. And if this is alpha, this is also alpha. Okay. And then the problem is that you get a 3D problem in this case. It's a 3D problem because, you know, you have the incoming wave that is incoming along this direction and reflected wave along this direction. So you, it's not just enough that you describe the wave along the x, you have also to describe the wave along the y, and therefore it becomes a 3D problem. And what I mentioned before, if you have an arbor that is converging, so you have an arbor that is like this, okay, and then you get your wave that is coming here, which means that the crest of the wave is something like this. What happens here? Okay, you get the full reflection here, from here, and in the same direction. But then you have a distributed reflection here, because there is a component that is perpendicular to of the wave, that is perpendicular to the side, which gets reflected. And therefore, again, this is a 3D problem. It is a 3D problem which generates, by the way, a further amplification of the wave crest, because you have several reflections that come together, and in a way, you have once again to describe the variability along x and along y. So if you have a rock, basically what you get is something like this. If you have a rocky coast, something like this, and then you have the wave getting into here, this direction. So you have a composition of various reflections, and various reflections that generate a 3D problem. But yes, that is also when you keep a rock. Yeah, probably. Any other question? Okay, now I want to move towards, first of all, we have only one lecture left. Okay, the lecture will be May 8th, and I will take your opinion on the course on May 8th. So if you are not attending by chance, it's not a huge problem because it can be compiled online. I will send you a reminder before the lecture, and I will tell you that during the lecture I will open the survey and will let it open a couple of days. And I will invite you to please compile it, because I really would like to get your feedback. And May 8th, I will also explain to you what is the meaning of the survey and how the university uses it. And I'm particularly interested in getting your critical comments. And you know that it's anonymous. And of course, you are two students only, so anonymity is not really, but I really would like to get your feedback on that. So next time, because we have few lectures only, and I wanted to make sure that you have a complete overview. Okay, perfect. Yeah.
I have a question about standing waves.
Yeah.
When the two waves have the same, the wave and the harbor has the same. It was what about
the same phase? I said.
Phase, okay, but it's amplitude.
Yeah. Okay. They have.
You can say the like describe the definition of standing waves.
Okay.
Then we have this standing waves.
Okay.
Can we describe that when it happens in a surrounded area of like lake?
Yes.
It's because stage lake.
Yes. Yes.
Or we can have it in our house by just put water in a bowl.
Yeah.
And apply force to see that. Yes.
Yeah.
It's like kind of standing wave.
Yes. Okay, let me just try to answer in the best way. So let me start with her question. Yes, you can create it in a tube, for instance, the tube in the bathroom. Do you understand what this is? Yeah. The old-fashioned approach. It is very easy because the tube has a regular side. It's very easy to generate the wave. And so if you in the tube, you generate the wave, you understand that there is a frequency when you generate the wave with your hands that causes the wave to continuously increase its amplitude. And then you may get to a point where you don't want to overflow, and you stop generating the wave, but still the wave continues for a while. And because the friction is very low, because of the tube, you have, it's very, very smooth. So the friction is low. But if you continue with the same period, then it overflows. The important thing is that you get the right period, because if you change the period, you know that the wave doesn't increase, because you go against the wave instead of pushing it. It's like the swing, the child with the swing, If you give the forcing at the right time, which is the dead hand, then with the same forcing, the child goes upper and upper. If you get the time wrong and you give the forcing when the child is still coming back, you stop it. So the important thing is the period of the force, which should be the same period of the pendulum for the swing, and in the tube, the period of the forcing must be the same characteristic period of the tube. Okay, so yes, this can be generated, and it is similar to the lakes, the seiches in the lake. We can call seiches also the waves in a bay, but typically we call seiches what happens in the lake. In the lake, typically the waves are generated by wind. The wind that periodically pushes, and usually the wind is not periodic, so the seiche is something that is not frequent. But if the wind gets a kind of periodicity, sometimes it happens, which is the same periodicity of the lake, then it can originate seiches. The mechanism is the same. It's a standing wave, but I tell you what is a standing wave. Then the mechanism is the same, and with the difference that there is no open mouth, and therefore you have antinodes at both sides. So the situation of lakes is this one. You have to look on the left here, closed basin. Okay. Now, what is a standing wave? Basically, if you get an incoming wave that is reflected, then the superimposition of the two waves generates, if it is fully reflected, meaning that it's the wave with the same equation, the only thing that changes is the minus plus sign before time. So the superimposition of the two waves is a standing wave. What is a standing wave? It's a wave that you don't see it traveling. It's just up and down. And then this happens with the simple application of these two equations. Okay, with the simple application of these two, I get it. With these two equations, 1 and 2. Because here these are equations of full reflection. The wave in this case doesn't change its phase, and there is only a change of the direction of traveling. Now, the complication is to make these equations such that you get a node at x equal to 0 and an antinode at x equal to capital L, where capital L is the length of the bay. And then in order to do that, you have to shift the x-axis of a proper quantity. That's it. But then the standing wave is generated by these equations. And there is no even need of mentioning the change of phase. I mean, these are two equations of pure reflection. So I'm not sure I answered your question. So is it a bit clearer now?
Yes, I think the frequency of two waves are the same.
Yes. Yeah, the frequency is the same. Let me just think of it. Yes, the frequency is the same. The frequency is the same. Yes.
So that makes it like double.
Yeah.
I think this.
Yes, the frequency is the same. And there is one thing. In order for the standing wave to generate, you need the frequency or period of the incoming wave, the period of the incoming wave to match the time required to travel back and forth. Because otherwise, what happens is that when the standing wave comes back, it crashes against the incoming wave and it stops. So there is no formation of a standing wave, because standing wave, by definition, is lasting forever. If you don't have damping, it's lasting forever. Actually, it is something that it's not easy to lecture, and this is why also I got confused. If you look for references, the references basically they give you the equations, but don't go into the details, into the real details, trying to explain physically what happens. You know, so it is something that I understand it is not easy to be understood, and for this reason, I think it is also interesting. It's fascinating. Any other question? Okay, let's move forward, and the next lecture is easy and short and easy, but let me just tell you a couple of things, information. So we are skipping climate change here, and we are skipping it because we already discussed it a little bit at the beginning. This is a discussion that is a bit longer, and but it is a narrative essentially. If you are interested, I think this is a nice lecture. It is a narrative that is, I mean, of course, I did it. I shouldn't say it's nice, but I think it is interesting and nice. It doesn't only talk of sea level. It also talks about floods, droughts, precipitation. But I leave this to you, and it's no material for the exam. Okay. I anticipate to you that probably we will also not discuss the last two links, but I will tell you, okay? And I leave the links there. I'm not removing them because I think it's an information that is interesting, but of course, we don't have time to talk about everything. So it is important that you take a note, meaning that I told you several times, for your exam, everything is here, but you have to remove the parts that we didn't discuss. And so far, the parts that we removed, besides something that we didn't remove, but I told you it's not relevant, like the first one for the exam is not relevant, and the other ones, I think they are all relevant. And now we are skipping climate change, for sure, and then we will probably skip the last two links. I'll confirm to you. Is it clear? So please take note, because otherwise, you know, you don't get oriented. You don't have to study everything. I think everything here is useful, but you don't need to study everything. Okay, now I would like to talk about beach protection. And the beach protection is something that you may think it's not very relevant to Harbour engineering, but actually it is. It is because very often when you you make a design project for an harbor, you also have to take care of the surrounding coastline, because an harbor is a perturbation of the morphodynamics, morpho-hydrodynamics of the beach. What is morpho-hydrodynamics or hydromorphodynamics? It's the composition of the dynamics of, one second, I just want to make sure that, yeah, okay. It's the composition of the dynamics of water, ocean water, and sediment transport. And sediment transport is shaping the morphology of the beaches. So you build an harbor, the harbor is a perturbation, and very often there is the need to intervene on the coastline close to the harbor, and in particular if there are beaches, this is even more important, intervene on the coastline to protect it or to recover it after the perturbation of the harbor. And this is quite a relevant feature, quite a relevant topic. Why beaches in particular? Because if the coastline is a rocky coastline, is a cliff coastline, of course you have less erosion. If you have beaches, beaches are formed by sediments that are transported by the currents, are transported by the waves, and therefore beaches are prone to erosion because erosion formed the beaches, erosion somewhere else, and then beaches are threatened by erosion. So an example of an intervention where the construction of an harbor impacted severely the beaches in the surrounding is given by let me see the link where it is. 1 second. And it's a video that we don't see. Okay, here it is. This project here. 1 second. Okay, the Tweed sand bypassing. It's a project to restore the coastline and the beaches after the construction of an harbor. So let's have a very quick look. It's in Australia. And so this is the situation. This is the harbor. Let me open the picture here. Okay, this is the harbor, which is built along a river. Now, the river in origin was flowing into the ocean freely, and now they built these walls. Why the walls? Because they wanted to make sure that the ships from the harbor could travel into the sea, of course, through the river. And actually, when a river flows into the ocean, very often there is, where the river and the ocean meet, the deposition of sediments and the formation of a bar. A bar, you know what is the bar? It's an elevation of the sea bottom. Because there is the confrontation between the river flow, which is bringing sediments, and the action of waves. And this is a problem, of course. It is a problem because the bar may not allow the navigation. And therefore, they built these walls in order to accompany the river into the beach. They extended into the sea. They extended the walls much further seaward than the beach, than the extension of the beach, because they wanted to go to a position with the walls where the bar cannot form anymore, because the sediment transport by waves is very strong in correspondence of the beach. But if you move into the sea, there is no sediment transport by waves. The sediment transport is operated by the waves after their breaking. And you know, the breaking occurs close to the coastline. So if you go deep into the sea, there is no sediment transport by waves, and therefore there is also no confrontation between the river and the waves, because in the open sea, the waves are just going up and down. They don't move in the direction of the beach. They move in the direction of the beach only after breaking. So there is no movement of fluid particles besides the up and down in the open ocean. So if you take these walls and you bring these walls seaward after the wave breaking line, then you avoid the bar. And they thought that this would be a good idea. And in fact, they did it. On the other hand, you see what happens. The sand becomes trapped behind the wall. So because the sediments here, typically the average movement is from the bottom to the up. And then after the river, there is erosion, because there is accretion of the beach, because the walls were trapping the sediment transport, along the coast sediment transport. And then behind the river, you have erosion. And the erosion continued also on the other side here. You see that the beaches are retreating here. And after also they built these groins, we will see what groins are, in order to stimulate accretion in the right part of the groin, but on the other part, behind the groin, the accretion is paid with an increased erosion. You see, after the groin, there is erosion. So they really had to devise something to take the sand from here, from the zone where sand is trapped, and bring it on the other side of the river. So what they built is a bypass, a sand bypass. And how the sand bypass is realized, you see here the new situation. This is the new situation after the sand bypass. You see that the beach has been accreted everywhere, okay? Nourished beaches. And the sand bypass is done through a pipe. Let's see. If you look at this video, it explains how it is done. And it is basically with a pipe that water is pumped through the pipe, and it's pumped with sand. So basically the pumps are pumping water mixed to sand, and they bring it on the other side. Jump through. So let me see if there are some pictures of the pipe. Okay, I leave to you exploring this this website. Okay, so this is why we are talking about beach protection, because we need to take care, as I said, of the surrounding coastline, surrounding an harbor. Okay, so basically we intervene over beaches to mitigate erosion, to resolve erosion. We usually get there, and we usually plan an intervention to replenish, to recover the beach after an erosion. So the first question may be why the erosion occurred. It may occur because there are local perturbation, like an harbor, like a wall that is a structure that is trapping the flux of the sediment. Because if there is a beach, the beach has been formed because there has been in the past a flux of sand, of sediments that settled down where now we see the beach. Typically, these sediments are brought by rivers, and then the waves displace the sediment along the coastline. And then, if we make a perturbation of the flux of the sediment, it may happen that where we had once the formation on the beach, we induce erosion. For several reasons. Erosion may also be induced by the fact that the beach lost its strength. For instance, because we modified it to make it usable for commercial purposes. So, for instance, if we remove the vegetation from the beach, because in nature, beaches are covered by vegetation. Only in the very proximity of the sea, we don't have vegetation. But as soon as we get a little bit further landward, then we get vegetation. And if the vegetation is removed, it's also another cause of possible erosion. So basically, we have to restore the beach, and we have several different alternatives. So first of all, let's see a classification of these alternatives. And we can classify. We have several different possible classifications. Let's classify first the interventions in terms of their physical effect on the beach. So the first the first element of this category is what we call managed retreat. It means that we accept that the beach is under erosion, and then we basically step back. So if we have a road, we put the road landward, we move the road landward. If we have buildings, we may decide to move the buildings, to relocate the buildings landward. In a way, we accept it. This is a solution that is particularly advisable when the erosion is massive, is something really important. And it is the solution that, for instance, is taken also for mitigating the risk of floods. When an area is a very high risk of flood, such that resolving the risk would require massive resources, we may decide to step back, to leave the area, and to leave the area at disposal of the river. Same thing here. If the sea erosion is something really important, something that we can't contrast, or we can contrast it, but only with massive resources, I mean, we may decide that it's rather better to leave the nature to make its own course, to allow the nature to evolve as they like, and retreat back. This is a first solution. Keep into account that usually this kind of solution is not liked by people and institutions for obvious reasons. Obvious reasons, okay? So if you are living there, you don't like to move for something that was created maybe by humans, human impact. Okay, second possible strategy, to hold the line. And this is a classical way. A classical way, I build a seawall in order to hold the line. Okay, so okay, there has been erosion, I fix a limit, build the seawall. This is something that it has been frequently used. As we see, we call it a passive measure because it's not intervening on the hydromorphodynamics of the beach. It's just fixing a limit, but we don't change the direction of currents, we don't change the flux of sediments, it's a passive measure, okay? And then there are interventions to move the shoreline forward in the seaward direction. This is an active measure. I am, in a way, trying to change the hydromorphodynamics, flux of sediments, direction of and strength of waves, in order to reestablish the profile of the beach. And then there are what we may call indirect measures, like, for instance, the development of vegetation and policies to control and limit causes they may have an harmful effect on the beach. So, for instance, you may set up a policy in order to avoid that people remove the sand from rivers or from beaches themselves. You know that, for instance, I went for the Easter break in Corse to make a visit. It's forbidden in Corse and in Sardinia to take any sand from the beach because, you know, tourists were used to, particularly in some nice beaches with nice colors of the sand, or a particular high quality sand, people were used like to fill a plastic bottle of sand to bring sand at home. And, you know, when you have a massive frequentation of people, they realized that this was causing a depletion of the sand over the beaches. So this is an example of a policy that was, it's not a structural intervention, it's an intervention in terms of policy making in order to in order to mitigate the problem, okay? So basically, interventions to hold the line and to move forward the shoreline are also called direct measures, as opposite to indirect measures. Okay, so you may divide these 4 points in, or let's say the last 3, in direct and indirect measures. Okay. Okay, and let's also point out that we often resolve the problem with infrastructures that are, or let's say, I think structure and or infrastructures that are located in the beach area. Okay. When we use structures, structural solutions, we could also hit them hard engineering methods, as opposed to nature-based solutions, green methods. Okay, it's important that we make, we highlight this difference, because nature-based solutions versus hard engineering are heavily discussed today. There is a lot of discussion on what is the best solution, and there are pros and cons for both of them. Okay, we will see something. But we don't discuss actually nature-based solutions, and nature-based solutions are like planting vegetation over the dune, or we don't discuss them because we don't have time actually. And so what are these measures? Sorry, the hard engineering methods can also be classified in 2 subcategories. Active measures. Active measures modify the flux of the sediments, modify the flux of water, modify the wave regime. And these are active measures. Active measures, we will see examples. And we may identify passive measures. Passive measures are interventions to hold the line, seawalls. Okay, because as I mentioned before, they don't change the flux of sediment or the wave regime. Example of active measures, which once again modify either the wave regime or the flux of sediment. Breakwaters, let's see a picture. This is a breakwater, okay? This is a breakwater. Typically, the breakwater is a structure that is parallel to the coastline. Its main direction, its longitudinal direction. So let's say the widest direction of the size of its size is parallel to the coastline. Okay, so it's elongated parallel to the coastline. This is a breakwater. What is the purpose of a breakwater? Stopping the waves, because erosion is caused by waves. So waves are coming from the open sea, and the breakwater is like a barrier. Okay, breakwater. Groins. Groins are, here there is a figure of groins. Groins are perpendicular to the main direction of the coastline. So they are not a barrier. And you may ask, but what is the difference then in terms of effect? Okay, it would be an interesting question. The breakwaters are mitigating the sediment of transport in the across shore direction. Across shore means in the direction that is perpendicular to the coastline. The breakwaters stop this flux of sediment. And therefore they avoid that the beach, the sand is transported away in the across shore direction. The groins, they stop the flux of sediment along shore. So basically they create, and you can perceive from this figure, an accretion updrift. Updrift means the side from which the sediment come. So the sediment are coming, they crash against the groin, and there is an accretion, an accumulation of sediments updrift, the direction from which the side from which the sediments are coming from. But downdrift, which is the other side, you get an increased erosion, of course, because you pay the expense. They are just modifying the flux. But you understand that if you put them in the right position, you can really modify the shape of the coastline in a way that the total amount of sediment trapped is increased. So basically, there are sediments that don't go downdrift much further because in any case, you trap all the sediments between the groins. Groins may be spelled with a Y or with a I, and it's a matter of American or UK English. I don't remember which one uses the Y. Another example of active measures is beach nourishment. This is active. And then it's actually beach nourishment may be associated to hard structures or not. And then we have the sand bypass, which is another active measure. And we discussed already what is the meaning. The passive measures include the seawalls and revetments. Revetments are coverage of the beach with boulders, for instance. And then berm protections. We discussed what is the berm. I think, I'm not sure if we discussed here in this course, but the berm is if the zone of the beach where you have accumulation of sediments. It's like the end of the wave run up, of the max wave run up. And the berm is a kind of protection. It's a tougher part of the beach. And then if we protect the berm, of course, we avoid the erosion. Okay, I think we can make now 15 minutes break up to 3 p.m. And then I teach up to 4:20. Okay, 4:20, 25. Good. Thank you. So good. Seawall and revetments. Just to give you an idea. So this is an example of revetments, and look at this figure. Here you can see a seawall with a combined with a revetment. So revetment means that you put in place over the beach material that protects the beach from erosion. And we have several different types of revetments that we can use. The revetments here you see big boulders can be done also by using gravel. Let me see. This is another example of a revetment. You see combination of wood infrastructure with filling material. And this is another example. You see this is small boulders. And here it's an example by using, I think these are tetrapods. It's artificial elements. They are called tetrapods because you see how it is the shape. They have 4 legs, basically. And they are structured in a way that they get linked easily with each other. And in this way, they offer more resistance to the action of waves. Because here, with the boulders, the risk is that these elements composing the revetment are transported away by the waves because, of course, they are placed in positions where we are concerned by erosion. There is a lot of erosion. And, you know, if you get an extreme storm, the problem is that if the revetment is taken away, then, of course, then under the revetment there is sand, and therefore the consequence, the impact can be extremely relevant. Okay, so now let's have a look at the direct measures and see how we can, what are the most typical interventions and how we can combine them. So this, let's have a look at this sketch here to start. 1 second, okay. In this sketch, you see the position, you see the legend on the right, upper right. The position of the original coastline is a thick black line. And with the emerging structure is represented, as you see, in the second element of the legend. And when the line is continuous, the structure is emerging. When the line is dashed, the structure is submerged or partially submerged. Partially submerged depending on the level of the tide, but in any case, the dashed line here indicates a structure that is at least sometimes submerged. And then you see how protected break are indicated, and then there is the emerging signal. The emerging signal is placed in correspondence of structures that are partially submerged, because in this way, the boats don't run the risk of getting a collision with the submerged breakwaters. So the seawall is the simplest structure. As you see, it's a straight line along the coastline, and the seawall is frequently adopted. It has some counterindication. First of all, it is a passive measure. So it is, if we need to restore a beach, it's not the right solution. And typically the seawall is adopted where we don't have a specific environment to protect seaward. It is meant to be a protection for the land, for the structures that are on the land, infrastructures like roads. But usually the seawall generates, seawards, generates an environment that is not really enjoyable. It's very close to the infrastructures that the seawall means to protect. So it is usually not a nice environment. If you look for a place where to swim and to enjoy the sea environment, usually you don't go just in proximity of a seawall. The seawall has also the problem that is reflecting the waves. Usually the seawall is vertical, and therefore it may generate a substantial and important wave reflection, which, you know, when you want to protect a coastal environment, reflection is not what you really like, because if you think of a natural coastal environment, it is shaped in a way to minimize reflection of waves, because it's gently sloping usually, and unless you are in presence of a rocky coastline, which has been shaped, has been shaped in, or let's say the environment of a rocky coastline is not directly threatened by the violence of waves, while if you have in the presence of beaches, which is the environment that we want to protect, usually you see that the beaches are organized in a way to minimize wave reflection. Another possibility, as I said, are breakwaters, and here you see emerging breakwaters, and the breaks can be protected. What does it mean, protection? It means that, as you can see, the break between a breakwater and the adjacent one, it's protected with a submerged structure. Submerged structure in order to, in a way, to save the break. But on the other hand, we don't want that erosion is concentrated in the break. You understand that structure like the breakwater that you see here, pictured here, the second picture starting from the top. A structure like this is concentrating the flow in the breaks. And if we are concerned by erosion, there might be a significant increased erosion within the breaks, and it may also cause the collapse of the breakwater. And therefore, sometimes we protect these breaks, not always, not always. First of all, the breaks are made because what is the problem with the breakwaters? The problem is, first of all, the visual. And in most of the cases in beaches, we want to preserve the visual. The natural looking of the sea environment is something that we want to preserve. And therefore, you understand, if you see a continuous barrier, you feel like you are into a prison. You feel like you can't see the skyline. And therefore, the breaks help to minimize the visual impact. So first of all, this is this problem. Second, you understand that the breakwater is creating like a pool between the coastline and the breakwater itself, with a reduced circulation of water. This is what we want. We want a reduced circulation, actually. But on the other hand, you understand that the water quality, if the breakwater is very long, can suffer from it. Can suffer because there is no circulation, so there is less oxygenation. There might be the concentration of pollutants with less circulation. And therefore, sometimes we make the breaks for the very reason that we want to make sure that there is still some circulation of water. On the other hand, we may want to protect these breaks. Now, when we are concerned by the visual appearance, what we can do is to put in place a submerged or partially submerged breakwater. And this is the third solution that you see here. And it is submerged means that, of course, they are still efficient in mitigating the energy of waves. They are still efficient in avoiding massive sediment transport. The fact that they are submerged, of course, implies that their efficiency in limiting the energy of waves is reduced with respect to an emerging breakwater. When the breakwater is submerged, usually we use signals in order, as I said, to alert the ships that of the presence of the breakwater. In this case, in this figure, the wrecks are also protected. So everything is submerged, but we see that there is a protection in the brakes. And here there is a combination with groins. In this way, we, in a way, integrate their actions in order to make sure that both a cross-shore sediment transport and a long-shore sediment transport are mitigated. And so it happens frequently that the two solutions are combined. Now let's talk about groins. We introduced groins, and we go to the number 4 figure. Perpendicular groins. Perpendicular groins are, as I said, conceived, are placed in order to avoid, to mitigate the longshore sediment transport. They can also be T-shaped. You understand that if the groin is T-shaped, then the efficiency of the structure to trap the sediment is increased. And a T-shaped groin is like a combination of a groin plus a breakwater. And therefore, of course, their trapping efficiency increases a lot. On the other hand, we need to take into account the fact that you know, the impact, the visual impact of a structure that is T-shaped is of course larger than a structure that is just linear, rectilinear. Another possible solution, which it is indeed quite often applied, is the creation of what are called here small islands. It means that if you create some emergence, some say small islands of boulders, for instance, with an irregular geometry, of course the visual appearance gains from that. And the only thing that you have to take into account is that a regular structure, it is easily predictable. The effect is easily predictable. When the structure is irregular, like the small islands that you see here, irregular means that the geometry, of course, it's varying. It's varying with frequent breaks. Predicting what is going to happen is much more difficult because these small islands generate three-dimensional effects, generate turbulence. While if you use regular structures like groins, like breakwaters, it is more predictable, the dynamics of the fluid flow, the dynamics of the sea water, it's more predictable. So we usually, when we decide for something that is unconventional, like small islands, something that is in a way less impacting, we should ideally take into account that make things like that in a way that we can ensure flexibility. I try to be clearer. These structures are difficult to decipher in terms of their effect. The best way to predict their effect is to realize the structures and see what happens. But if we adopt this strategy, we need to make sure that we have the opportunity later on to change things, to integrate the structure, maybe like to change the shape of these islands. And this is a good strategy. Of course, it's a good strategy if you don't have a urgent problem to solve, because it may be a trial and error procedure. Instead, if you have a urgent problem to solve and you need to be quite safe that at the first attempt you go to target, then it's better to use regular structures. And, you know, there is also to say that we have a lot of experience on the effect of groins, the effect of breakwaters, the effect of structures that were repeatedly tested. When you invent something different, something that indeed more creative, which means that it's probably less impacting, then you have to take into account the increased uncertainty of the intervention, and therefore flexibility is a way to make sure that you can make corrections. Okay, this is the discussion that I wanted to propose about the structures. Now let's talk about beach replenishment. Beach replenishment can be associated to structures because it's clear, if you just put sand there and you don't make any change, any significant change in the beach hydromorphodynamics, then the replenishment is going to be eroded. Like the original sediment was eroded, the replenishment is probably going to be eroded again, unless with the replenishment you succeed in making a change in the circulation of the currents, in the circulation of waves. But this is unlikely to be successful if you just work with the replenishment. And therefore, it may be appropriate that you protect the replenishment with groins, like in the second figure that you see here, or submerged structures. A relevant question, you see here then first the replenishment alone, and then the replenishment associated to groins and submerged breakwaters with protected breaks. And then in this case, we have the replenishment associated with groin and partially submerged groins, because the groins can be sloped seaward so that they, in a way, after a while get submerged. And in this case, you see in the second figure also the association with a breakwater. And basically, in the third part, you see the replenishment protected with groins or T-shaped groins. A relevant question about replenishment: the diameter of the sand, the size of the sand grains, and in general, a relevant question, where to take the sand? Because it looks like the sand, all the types of sands are the same, are similar, but it's not like that. Any beach has its specific sand size, its specific sand color, and also composition of sand in terms of minerals, in terms of several other inherent behavior of the sand. And it turns out that when you put a replenishment in place, people can notice that it's not the original sand because, as I said, there are different features. There might be different features. And you cannot take the sand from the same place because it was eroded. So there is a question on, indeed, on where, and we should make sure that we take a sand that is as close as possible to the original one. Second, there is the question of the size. Indeed, when we put sand back, it may be advisable that we use grains with larger size in order to limit erosion. On the other hand, clearly, if you use larger grains, the difference becomes clearly visible. And therefore, it may be questionable whether it is appropriate such a solution rather than a solution that uses a completely different coverage, like revetments. because I mean, sometimes, as you know, when you cannot match precisely two patterns, instead of putting together two patterns that are almost the same, it may be better to create a discontinuity. And this is like with the suits, you know, when you don't have two suits of the same color, then instead of a small difference between the jacket and the trousers, it may be better to make a complete, what we call in Italian spezzato, which means that you make a big difference between the two. And so it is indeed replenishment. It's something that may look really nice, interesting, because in a way it is reconstructing, restoring the original environment. On the other hand, it has been to be carefully considered because of the duration, because of the association with structures and the type of material. And also keep in mind that sand is really a precious material. It's a protected material. So and it is not easy indeed to collect it, especially because sometimes we need huge volumes. Okay, and let me see if I have something more to, you see here, something more to say. However, one should not underestimate the impact of beach nourishment. This is what I was just discussing now. Now, peculiarities and limitations of breakwaters and groins. Breakwater and groins are widely used, and if you go in the beaches here of the Adriatic Sea, you will see a lot of them. It is interesting also to go there and to look at the effect. So the changes in the beach morphology. And this is also very useful if you have to design a project, because you know, these are structures that are difficult to model because their effect is an effect on beach hydromorphodynamics. And typically these are three-dimensional processes. It is really not easy to model what will happen. We will see some examples, but it is indeed not easy to model what will happen when after a groin or a backwater are built. And the best way to get an idea of what is going to happen is to look at what happened in similar environments after the intervention has been realized. So it is useful indeed to go over a beach and see what people did and what is the result of their intervention, because it helps you in gaining an expectation that is very useful when you are involved in a design project. And sometimes they are combined, even if, as I said, the visual appearance is something that has to be evaluated carefully. Okay, finally, for this lecture, a few more words on nature-based solutions. And let me just seek another link, because I didn't want to make it a long story here, because I mean, beach protection is not our main focus, but I want to show you a couple of pictures. So 1 second. Let's take coastal engineering here, and then here nature-based solutions. Let's forget about this. This is an example of vegetation put back into a dune. So if you look at this beach here, the figure is quite interesting. So this is the berm. You see where you see some relicts, you see some deposition of debris. This debris get settled down at the limit of the wave run-up. So there is the wave run-up along this zone here, okay, which is also called the swash zone. So the zone of the beach that is usually covered by the wave run-up, wave getting back and forth, is called the swash zone. At the end of a swash zone, where, let's say, the most frequent waves get up to, you get the burn, because where the run-up of the most frequent waves ends, you have the deposition of the sediments, the largest one that are transported by the waves. This is why you see woody debris here. And as a result, the berm is composed by material that has higher strength, and therefore it's a protection. It's a protection from erosion, because of course to erode the berm, you need more power.
Are they like rocks?
No, not really rocks, because the berm is not material that is very heavy, because these sediments are transported by waves that are quite frequent, not very energetic waves. The energetic waves, the most energetic waves, actually they form the dune. So in the dune, you may find also some boulders, if there are boulders around to be transported. And the dune is the limit of the most extreme waves. The dune gets formed by the very extreme waves. And usually over the dune, you don't have water frequently. The dune has an higher elevation, because why? Because the most extreme waves bring a lot of sediments. They have the capability to transport a lot of sediments because they have a lot of energy. And therefore, this is why the dune is more elevated. And the fact that it's more elevated makes the dune adapt for vegetation, because the dune, given its elevation, can collect fresh water. And therefore, over the dune, naturally, you have vegetation. In the bottom of this picture, you see that there is a lot of vegetation during the dune, over the dune, but in some cases, it may be destroyed by humans, by human intervention, because typically you don't see dunes in the commercial beaches of the Adriatic Sea, not because they were not there. If you go over beaches that are free, not managed, then you will see the dune. But for where there is the intention, the will of making a commercial use of the beach, usually the dune is removed, because the dune is an obstacle. It's something that is really not useful. It is something that you can't use for commercial purposes. And therefore, sometimes it happens that people remove the vegetation, or maybe that you get an extreme event, a very extreme one that removes the vegetation. And therefore, one possible solution is to bring vegetation back. Here, or maybe also the animals. Here they put this kind of, I don't remember the English name of this. It's okay. It's a limitation to access that is conceived for animals in particular. And because the animals may also destroy the dune and destroy the vegetation. Vegetation is indeed a strong protection. If the vegetation gets really dense, it's a strong protection. And it offers also protection against wind, because erosion is made not only by water, also by wind. And we can look for some images of dune vegetation. And you see that in some of the cases it's much developed. You see here, or here. You see this vegetation makes the dune stronger. This is a classic. We see several times this kind of vegetation that is annual. And then, like, okay, we already saw this. There are several figures here. This is a schematic. And sometimes you can find a sequence of dunes, more than one, because they are formed by different processes, depending on the extreme character of the process of the storm. Then they can form several different dunes. Or you can see here, you see the vegetation is quite developed. You know, sometimes it's just enough that you get a few meters over the sea level and you get a deposit of fresh water, a storage of fresh water. Where you see vegetation, it means fresh water. Otherwise, you don't get any vegetation. But you know, it's a significant storage. The sand is, with its porosity, is a significant storage. And you see here there is the bar, the berm, and then there is the dune, and here there is a second one. And it happens frequently that you have some channels, like it is called, the first one between the berm and the dune is called the runnel. And these depressed areas between one elevation and the next one, and they are quite typical. Okay, I mean, did you want to take a picture? Okay. Anyway, it's interesting to consider these interventions. This is the same vegetation that you saw here after a while. It is interesting. In a way, these solutions are really interesting. The only problem is that, and I want to conclude this discussion with this consideration. When you build an art structure, it is more easily predictable, its effect, rather than a nature-based solution. Because an art structure has a geometry that you shape, has it's durable. It is something that usually lasts for a long time. It is something durable. And therefore, its effect is more predictable. And what is the result? The result is that the design project is easier. You may have quantitative methods for design. So when I have to design a breakwater, the methods are well consolidated. Some of them are empirical. Because the complex is, the process is three-dimensional, so it's a complex process. So the methods may be empirical, but nevertheless, they are well tested. And they are accepted in a quantitative way. You can find textbooks, manuals, suggesting how to build a breakwater. We will see that we have quantitative guidelines. With nature-based solutions, the fact that their effect, they don't have a regular geometry, their properties are less known. If I build a wall in concrete, I know the mechanical properties quite well. For deciphering the mechanical property of properties of a tree or of a given species, this is problematic because they depend strongly on the local condition, on the wealth, on the health of the plant. They are difficult to decipher. So the result is that you don't have technical guidelines for designing them. And this is something that indeed it's a limitation. And also the duration is something that is not known. So when you basically restore a vegetation cover, how long it will resist? And it is a bit problematic. So the recommendation that I would like to give to you is, in this case as well, keep some flexibility. Like, okay, I decide to protect a dune with new vegetation, with a nature-based solution. is it possible to maybe integrate with something that may serve as a backup plan? Like, for instance, sandbags. A possible way to restore dunes is also to use bags of sand, and which may be realized in geotextiles, in a material that is organic in a way. And therefore, but on the other hand, it's organic material that has quite well-known mechanical properties, because we can test into the lab the properties of sandbags, of organic materials, selected organic materials. So is it possible to make an integration of different measures? Or is it possible to conceive a plan B already from the beginning? Like, okay, I put vegetation. If after 6 months vegetation dies, what is the backup solution? Something that you should take into account, because with the nature-based solution there is this important drawback. And so sometimes the engineer is a bit reluctant to use these solutions. But the reason is not the fact that engineers don't like the environment, don't like nature. The reason is that the engineer is concerned by their responsibility, direct responsibility in the design, and therefore they may decide to apply a safer solution. And a structure, indeed, it's a safer solution. Okay. Good. By the way, I think you heard of what happened yesterday at the reservoir in Suviana Lake. I can't understand how a turbine could explode. Did you get any information on that? I read on the newspaper in the morning, but still, I think that, no, I mean, there is nothing to laugh, indeed. But I think that nobody knows what is the reason. I can't really understand how a turbine can explode. I don't know, because there shouldn't be any oil in that. Any oil, I mean, any fire. No, I think there is a lot of electricity, but of course, because it is a I mean, the power of this hydroelectric power is really significant. It's a lot of power. This was a new turbine, so maybe that the power caused the explosion, but for sure, I think it is something related to power. There shouldn't be any gas, any fuel there. I really don't understand. And it is a pity, because, I think these plants are important, and they are green solutions indeed. And, if people get a bit concerned by these plants, it's not a good thing. Because people usually are a bit concerned by reservoirs, and this is something that didn't happen to the reservoir itself. It happened to the machinery, but still, I'm sorry of that, because indeed it is something that I can't really understand how it could happen. Okay, let's go back. And then we can go forward with something more quantitative. So this one was basically a narrative, okay? And something more quantitative, sorry. Something more related to design. And I decided to focus on groins. The reason why I give priority to groins is that usually Professor Archetti dedicates some time to breakwaters. And therefore we took this agreement, and I put breakwaters as my last link, which we will probably not use, as I said. And I also made sure that in this link here, whenever it is used, I don't overlap with Professor Archetti. But we agreed that I would take care of groins. So when you design these structures, let me take a picture just by chance of a groin. Maybe that this groin is misleading. Groin. Okay, better. Okay, let's have a look across these pictures. This is indeed a groin. 1 second. It's a woody groin. Okay, so let's look at this one. We can't, just 1 second. Okay, let's look at here. Oh, this is much better. This is a woody groin. It is permeable. So a feature of groins is permeability. Permeability, you understand what it means. It means can on a long shore current pass through the groin or not. In this case, it can. And we can't see what is the shape of the structure below the sand because this is partially covered. So in a way, what it's important to notice here is indeed the permeability. So the groin may be open, may have windows, and permeability helps in reducing the impact. On the other hand, of course, it decreases the efficiency. This is another example. Let's see if we can get it. Okay, let's close it. Let's look it here. Okay. Now, let's look it here. And this is another example. Again, it's permeable. And the nice thing is that when they are woody structures, of course, they are more environmentally friendly. This is another example. This is on Wikipedia. Okay, this is a groin with made by boulders. So the first question is, what material should I use? And a groin like this one is also partially permeable. If you don't put a core in it, so a solid, a more, let's say, a more impermeable, a more impervious structure in the inner part, if you don't put a core in it, it's always permeable. So the first question is, how should I what material should I use? And look at the effect here. So the wave is coming from the right to the left. Okay, the wave is traveling from the right to the left. The groin has induced an accretion, updrift. So this is updrift, and an erosion, or let's say less accretion, downdrift. This is what you expect. If the sediment is coming from here, look at my mouse, then the sediment gets trapped updrift, and downdrift, there is less accumulation, which may turn into an erosion. There is always a dominant direction of waves. So, I mean, in this case, it was clearly chosen the orientation also of the groin by taking into account that the direction of waves that we see on the screen probably is the dominant one. And look at the inclination of the groin, cannot be really understood from this picture, but the feeling is that the groin is oriented so to be perpendicular to the wave crest, to the direction of the wave crest. And this is done in order to maximize the trapping effect. Okay. Let's see this is another example from Wikipedia, woody groin, nicer. And here you see that the permeability is reduced with respect to the other example that we saw. Let me go back. Okay, we already discussed this picture here. And then here there is, no, it doesn't. Okay, one thing, submerged groin warning. This is for ships, and keep off the groins. And this is just to avoid the risk of falling. On the other hand, the groins may induce something like this part. Okay, here you have the coastline, and let's suppose that will be the two groins here. Okay. If the groins are very close, they may originate what is called a rip current. The rip current is a current that originates circulation of water like this. And if the groins are very close, the fact that the water cannot go through the groin, this cannot happen, right? Basically, you obtain a concentration of the flow in the direction of the groins. And then the street current may be extremely dangerous because if you burst here and you go there to swim, you may be transported seaward. So if we look for rip currents, you see, this is without groins. This is created by the morphology of the sea bottom. But you see, know your options. If you are caught in a rip current, relax. Rip currents don't pull you underwater. Don't swim against the current. They are extremely dangerous. And you see here an example, a picture, a nice picture where you can clearly see a rip current here or here. And they can be induced by groins. And there are interesting videos how to spot a rip current. In Australia, in particular, they experience a lot of rip currents. You see here with the colors. Okay. Interesting. Okay, so other example of groins. This seems to be along a river. They are also used along rivers to protect from erosion the river bank. This is another example. This seems to be along a river as well. Okay, it's the Rhine River. And this is another woody debris, woody groin again. And with boulders. This is along the river. With boulders, I think maybe artificial boulders. This is a permeable groin, which is also used as a pier, not really a pier, as a kind of walk for fishermen and tourists. And this is a combination of a revetment and groins. This is New Zealand. You see growing here. in order to protect the bay entrance, and that's it. Now, the question is how to design these, of course. So let's see if, where is my website, design of drawings. Just 1 second, because I think. Let me make a call, I'm sorry, because this one is, give me 1 minute, it's very quick. Buongiorno, sono Alberto Montanari, ho visto una chiamata, anzi 2. Sì, grazie. Sì, buongiorno, mi scusi, non potevo rispondere. Sono Alberto Montanari, mi dica. Sì? Sì? Dunque, mi aveva detto che forse dobbiamo passare, quindi, perché mi aveva detto che forse potevamo procedere via mail. Perché? Sì, gliele rimando firmate, sì. Le scannerizzo o posso fare firma digitale? Meglio che le scannerizzi, come mi dice lei. Va bene, perfetto. Tutti e 3, perfetto. Quindi è lo stesso documento firmato da tutti e 3. Va bene, perfetto. Sì, esattamente. Grazie. Buona giornata, arrivederci. I apologize. Okay, so design of drawings. First of all, as you can see here, there is the shape of the groins may be articulated. We already talked about rectilinear groins and the T-shaped. And in this case, you see groins that have this V feature, this V shape. And you can clearly see the effect on the beach and the accretion that was originated by the groins. And the design should take into account the evolution of the coastline after the construction of the groin, because the groin is trapping on one side, updrift, as I said, sediments, and at the expense of the side downdrift. So downdrift, we may expect an erosion, which is anyway, as you see in this figure, compensated by the next accretion. So what you obtain is a moon-shaped coastline. And of course, you have to design the size of the groins, the length, and the distance between them along the coastline in order to make sure that you have a solution that is effective. And in order to do that, what you have to understand, to predict, is, as I said, the evolution of the coastline. What is driving this evolution? Again, the dynamics of water and sediments. So it turns out that if you want to make this successful prediction, you have to use a model that is simulating the hydromorphodynamics of the beach. And you understand that this is something indeed complicated, with a lot of turbulence, and therefore a lot of complexity, a lot of chaos. So I mean, the problem is an interesting problem. Fortunately, the problem is typically three-dimensional. You understand why? I mean, it's a problem that is characterized by variability in the three dimensions of space. And therefore, the numerical modeling is complicated. Fortunately, we have a lot of experience in realizing this type of interventions, which means that we can benefit from it through empirical formulas. So our purpose together is to have a look at these empirical approaches, which can support a kind of preliminary design, can support the development of a preliminary idea, a preliminary size of the groins, a preliminary spacing, which in most complicated cases may be verified through a complete numerical model. But first, we need to discuss what is our perception, what is our empirical and holistic understanding in order to derive this preliminary design. So, first of all, once again, keep in mind that groins are effective in mitigating the impact of along-shore sediment transport, so sediment that move along the coastline. Okay, perfect. Now, what type of groins are usually used? First of all, let's make a first classification, which divides them in two categories, long or short groins. So if you go with the structure, with the groin, across the full surf zone, the surf zone is the zone where people go surfing. So it's the zone that is included between the coastline and the average wave breaking lines. Breaking means where the wave transform their energy into kinetic energy. So if you go across the whole surf zone, we call the groin long. The surf zone is where there is sediment transport. So if you go across all the zone of the sediment transport, it's a long groin. If we cover only part of it, it's a short groin. And you understand the difference. The difference is clear. A short groin is less impacting, but it's also less effective. And he is capturing only part of the sediment transport. Okay, and keep in mind that it depends, this classification, like the position of the breaker line, etc., depends on the wave regime and on the seasonality of the wave regime. So some groins may be long in the summer season and short in the winter season. And also the position of the wave breaker line and therefore the position of the surf zone may change during the year. But you understand that when we make this classification, we refer to an average situation. And then there is another classification which we need to introduce, which divides the groin in high or low, depending on the height of their crest. So high groins have crest elevation that is always above the sea level, even during high tide. Conversely, the low groins are those that are at least during some time submerged. I mean, high groin are of course more effective, and on the other hand, they are more impacting also on the visual. Okay. Okay. Now let's see. Keep in mind that an obvious consideration, shore sediment transport is also important, may be important. And in particular, let's make a consideration on the time scale. The longshore sediment transport is the sediment transport that is governed by, let's call it the normal wave regime. So it's a slow process. It's a more continuous process, which may be governed by those wave directions that last for a longer time, for those waves that last for a longer time. So the longshore sediment transport is determined by kind of average conditions. The across-shore sediment transport typically is governed by short and extreme storms. Short and extreme storms. And therefore, you can also understand what is the contribution given by these two structures, breakwater and groins, with respect to the sediment transport and the type of events. Breakwater are more effective on the huge storms, on the violent storms. Groins are more effective on the ordinary regime, let's say. Okay, now I think we can, we already discussed this. Permeability. So, depending on the type of effect that we want to generate, we may decide to allow for certain permeability. And the decision must be based on a preliminary consideration of the time scale of your intervention. Do you want to originate an immediate solution, urgent? Do you need a urgent solution, or do you need an intervention that is, on the one hand, less impactful, but on the other hand, may take a longer time to restore, to give a solution to the situation that you want to mitigate? Another consideration to make is that are you concerned by other features like rip currents that may be generated by groins that are less permeable, more permeable? What you have to consider is that if you give some permeability, your intervention is less effective in changing the environmental condition, but on the other hand, it is a smoother intervention. It is something that may allow you to test a preliminary solution, to test an intermediate solution. So depending on the permeability that you decide to give, you obtain different effects. And there is also the possibility to quantitatively estimate the effect of introducing a permeability, as we will see. If normally, if a groin is built by using huge boulders, normally they are not much permeable. We can allow for some permeability even in this case, but usually these groins, when they are realized with boulders, it is because we need to reduce permeability. And in order to make them not permeable, usually, as I said, we build a core in the central part of the groin, a core that is made up by material that is not permeable. And on the other hand, if we want to allow permeability, usually we use woody groins. Perfect. Now, what we need to do preliminarily in order to decide what is the best type of groin to use is to make a preliminary assessment of wave regime. statistical assessment. So you have to define the dominant wave direction or dominant directions, plural, and to identify a wave height, an expected wave height for each direction, etc. And then, basing on an estimation also of the sediment transport dynamics, which depends on the energy of the waves and the direction of the waves, basing on this information, you can carry out your design. What I want to do today, before we break, waiting for the next lecture, is to introduce what is an empirical but quantitative concept that may drive your preliminary design. And keep in mind that here there are some considerations regarding the timeline. And, you know, in some of the cases, in our experience, we found that after 3 decades, after more than 30 years, some beaches protected with groins were still evolving. So, I mean, the time scale of the intervention, which depends on permeability, is indeed important. So I said a quantitative, still empirical, but quantitative approach to groin design. First of all, there are several parameters that need to be designed, which are basically the geometry of the groin, its length, its spacing, its elevation, its porosity, which has an effect on permeability, and tapering. Tapering is how you shape the groin in the direction of perpendicular to the coastline. So this is a tapered groin. This is tapered, and this is not tapered. Okay. And the angle to the shoreline and the shape, straight, angle, T-head, spewed, etc. Now, we also have the parameters like depth at the tip of the groin. The tip is the end towards the sea. And the beach morphology is also important because clearly the slope of the beach, for instance, it's an important parameter, the position of the berm, etc. The depth at the average breaker line or beach closure, the sediment availability, grain size and variability, sediment density. And also we need to consider these parameters related to waves, so wave height, wave period, wave direction, as I said, wind, etc. And here is the rule that I wanted to introduce. We have 10 minutes, so we are in time. So preliminary design is often carried out by following the so-called 1/3 rule or lambda shoreline rule. It's a rule of thumb. Okay. It is very simple. And keep in mind 1/3. 1/3 is helping you also to remember. So what does the rule say? The rule says that at the post-project coastline, post-project, after the groin, coastline, during mean low water level, okay, mean low water level, it means low tide on average. So when you have the average low tide, you can identify a position of the coastline, okay? Good. This coastline is located about between 1/3 and 2/3 of the distance between adjacent groins measured behind the structured seaward face. So, let me put a figure on the screen, and then I redraw the figure on the blackboard. This is the figure. Let's refer to, let's forget about the T-shaped groin for now. This is the, how it's called here, it's called the pre-project coastline. Pre-project project. Coastline. Okay, perfect. Now we make the drawings here. And another one here. And let's indicate with L, no, G. G is the gap. G stands for gap here. This is the gap. The new coastline, how it's called there, it's called, okay, let's call it the new coastline. It's placed at a distance from the tip here. That is about 1/3 G. Let's see if everything is, yeah. Okay, let's forget about the high water shoreline that is shown there. Let's look at the figure only for the low water shoreline. And therefore, if you measure a distance, lambda G, where lambda is 1/3, you get the position of the new coastline. It's very simple. Okay, actually, we may say that 2/3, sorry, lambda is comprised 1/3 and 2/3. 1/3 is the prudent, not really the prudent, because, okay, between 1/3 and 2/3. So it's very simple. And this is the rule of thumb. By using this rule of thumb, you understand that once that you fix the position of the new coastline, and again, this is low water shoreline. So keep in mind that with the high tide, you get a little bit back with it, okay? So once that you fix your target, I want to advance like 10 meters, okay? You know that if you want to advance 10 meters, then you have to limit the drawing with the length and spacing so that you obtain this result, advancing 10 meters. And you understand that you have 2 degrees of freedom. If you take this rule of thumb entirely, we have 2 degrees of freedom, length and spacing. Okay. If the drawings are longer, you can increase spacing. And if you look at the figure above, the figure is saying something more, but let's forget about the T-shaped drawing for now. Because the figure says that the actual coastline is not really rectilinear after the construction of the drawings. Of course, we don't expect something that is perfectly straight. And what we expect is, in particular, if we go also on the side, on the other side of the left drawing, what we expect is that if the waves are coming in this direction, what we have is something like moon shape, as I said, something like this. And then here again, it's something moon shaped. So this is quite simple, and of course we have 2 degrees of freedom. And then we can use additional considerations in order to limit the variability of these 2 degrees of freedom. For instance, one suggestion that is frequently given is that the gap shouldn't be less than 20 meters. 20 meters is really reduced. You understand that if you go over a beach, which you can see drawings at 20 meters, it's quite, I mean, quite massive. It's quite a massive intervention. So usually we recommend not to go with gaps that are lower than 20 meters. And therefore, if you put some limitation on the spacing, then of course you get additional indications on the length that is required. On the other hand, we also say that the groin shouldn't be too short, because if it is too short, you understand that it's something that it's not really useful. So less than 10 meters of length of the groin is something that it's not really helping a lot, because you would need to put them very close in order to get a successful intervention. So this is the basic rule, the lambda 1/3, and this is quite a classic question at the exam. So pay attention, because you understand it's something that is relatively simple. Question? Yeah? Sorry, say again.
It's a way.
No, it's not determined by, it's not a wave and not, this is seen from above. It is the shape of the coastline, the actual shape after the intervention. And because it's not rectilinear, you have, this one is the direction of the waves seen from the top. And this is the displacement of the sand after the position, because the waves are bringing the sand in this direction, so the sand is accumulating here. And then you see, if the sand is accumulating here, for compensation, you need to get some erosion on the downdrift side. Is it clear? I'm not sure. Did I reply? Yeah, perfect. Other questions? No questions. So let me just check for the previous slides. Okay. So an additional consideration. We may have larger values of lambda, which may even exceed 2/3, and they may be appropriate for very energetic environments. Larger distances between groins, uncertainty, long-term sediment supply, etc., etc. So, I mean, you see also the variability between 1/3 and 2/3. It depends, it's governed, this variability, by the energy that we expect from the given environment. So if it is very energetic, you will take 2/3. 2/3, you understand, it means that it is less effective, your intervention. If you increase, if you bring back the new coastline, the intervention is less effective. And it depends on the energy. So you make an evaluation of what you expect in terms of waves, in terms of energy of the waves. And let me see here. Okay, a final consideration. This rule is considered applicable, so it's considered representative in the situation where the angle between the wave crest and the line connecting the tips of the groin is small. So let's show it here. So the line that connects the tip of the groin is this one. And this is the wave direction. And this is the angle here. Or let me say, because it gives a value, I want lower than 25/30. Okay. So it means that the max of the effectivity is, okay, this is the angle. Lower than, okay. So if the waves are rightly colliding with the groin, so the waves go against the groin, the intervention is effective. If the waves are traveling parallel to the groins, it's not effective in trapping the long short sediment transport. Okay. Good. Any question? Okay, so see you on May 8th. May 8th is our last lecture. I will give to you the survey to compile. I will give you 15 minutes time during the lecture to compile it, but if you're not attending, you may fill it online in the time interval. As I said, I will let it open for a couple of days. And May 15, we will confirm to you the exam date, okay? One thing, if you take the exam May 15, what we discuss on May 8 will not be asked entirely, will not be, I will try to avoid the questions, complicated questions that I will teach related to things that I will teach on May 8, okay? So is it clear what I'm saying? Because I want to give you time. If you wait and you take the exam in June, then you will have to study everything. Okay, good. Thank you very much.